He's just coming down.
I know they're supposed to generate a superextension here.
Okay, so our first speaker this afternoon is Sean Keel, who's going to talk about mirror symmetry made easy.
All right, so here's the. This is all joint work with Paul Hacking. So it's a joint with Hacking and Gross. The theorem I want to. So I'm going to talk about following conjecture, which is a theorem in dimension 2. I'll state the thing, and then of course I'll explain all the terms that appear in it. So the theorem says that U is going to be an affine Calabi-Yau variety with maximal boundary. I'll have to define what that means. That's one of our things with maximal boundary. Then what I want to show is, then the claim is that, first of all, if I look at the functions on U, so it's an affine variety, so it has lots of functions. Look at the ring of functions. But think of it just as a vector space. This has a canonical vector space basis. It's not quite a basis, put it in quotes. It's up to scaling. And secondly, if I look at the multiplication rule on the vector space, so this is a ring. It's a C algebra. As a vector space, it has a canonical basis. Then I can ask, okay, what's the multiplication rule, say, in this canonical basis? The multiplication rule in the canonical on the vector space is given by counts of rational curves on the mirror. Curves on the mirror. Okay, so I want to explain how this goes. So first of all, what do I mean by Calabi-Yau with maximal boundary? So let's say I have YD, where this is a smooth projective variety. And let's say this is a normal crossing divisor. And we're thinking of this as a compactification of U. So U is going to be Y minus D. Okay, so I've compactified U by in this way. And then let's think about differential forms on Y with simple poles along D. So this means, R is always going to be the dimension of Y, which is also the dimension of U. So these are just R forms, but they are allowed to have poles with, at worst, simple poles allowed along D. Sorry? No, D is nothing. D is just a normal crossing divisor. So I just have Y is a smooth projective variety. D is a normal crossing divisor on Y. No, that's up here. Here, this is a. That's going to be the thing we're going to get to. Here, U is just the complement of. So I'm going to define what it means to be a Calabi-Yau next. But no, it's not affine yet. So these are R forms on Y with where I allow poles along D. Of course, by restriction, those live inside of all the forms. If I restrict these to U, they don't have any forms, so they're just a particular bunch of holomorphic forms on U. And the fact, which I think is due to Yataka, is that this subspace, this vector subspace of this thing, is actually canonical. It's intrinsic to U. Is intrinsic to U. It does not depend on the compactification. It's independent of the compactification of U I chose. Compactification of U we took. So these are the natural forms on if the thing is possibly open, which this would if I have some non-compact variety, these are the natural forms to look at. There's this finite dimensional subspace that's canonical, that's canonically associated with it, and our definition will be, these are what are called the log forms, by the way. These are called log forms, and the definition, I'll say that U is Calabi-Yau. It should really be log Calabi-Yau. If this space is one-dimensional, this subspace, this vector space is one-dimensional, generated by a volume form. By a volume form. That's implied by, and if I just use some fancier words from the minimal model program, it would be equivalent to, so we'll just say it's equivalent to saying that I can choose such a compactification. I can find YD such that omega has a simple pole along each boundary component, along each component of D. Each component of D. And in this case, so what do I say by omega? So it's one-dimensional. We're saying that the log forms are just a one-dimensional space generated by a volume form omega, which is now, of course, unique up to scaling. So that's the definition of Calabi-Yau. And another way of saying it is, what you have is you have a variety U, which can be compactified to some projective variety with a normal crossing divisor, such that you have a volume form on U, which has a simple pole along each component of the compactification. That's another way of saying the same thing. So we call YD a minimal model. A minimal model of U. There will always be, except when this thing is essentially compact, there will in general be infinitely many for any given U. We'll be looking at all of these, so for any U. Okay. And finally, what do I mean by, I'll give you loads of examples here in a minute. I'll just get there's just a couple more, maybe one more object I have to define, then I'll give you loads of concrete examples. What is maximal boundary? I'll say U has maximal boundary. Well, at the moment, notice, at the moment I could take U to just be a compact Calabi-Yau manifold. That would satisfy all this. D would just be empty. U would equal Y. Maximum boundary is supposed to be the opposite extreme from that. So as far away from compact as you can get. What should that mean? I'll say U has maximal boundary if there exists a minimal model YD, and a point, and what's called a zero stratum, and a zero stratum of D, i.e., a point P in D, which lives in Y, which looks like 0 living in the coordinate axes, inside of CR, i.e., the coordinate planes. Yeah, thanks. I.e., I have analytic coordinates, analytic coordinates, Z1, ZR for Y near P, such that D is given by the product, ZR equals 0. It has, what we're saying is, it has the boundary has normal crossings. How many possible components of something of normal crossings could you have? Because they're normal crossings, you could have as many as the dimension. I want to assume I have a point with as many components as possible. So this is sort of as far away from compact as you could get. And now let me give you one last technical definition, and then I'll get to the examples. So this is the key definition. So I said that there is the key idea of this thing is that a Calabi-Yau manifold has a canonical basis of functions. That's what I'm trying to show. So if you live on one of these things, maybe I could have just said, what's an upshot of this? What's an informally, what the first one says, you can say is, if you live on a Calabi-Yau, well, of this particular kind, then there exists an intrinsic GPS system in your world. That's what I'm saying. There are just canonical functions that are around that tell you exactly where you are. There's enough functions, canonical functions, to determine each point. And that this is potentially interesting because, according to some of you all, we live on a Calabi-Yau. So, okay, so the key definition, again, now U is Calabi-Yau with maximal boundary. I don't really need maximal boundary for this definition, but it won't behave well without it. I call it the tropicalization of U. And this is going to be the set of all pairs EM, where E is a boundary divisor in some minimal model. Minimal model. I'll give you, lots of examples to see this if you've never played with such things. And M is just a positive integer. And I'll throw in one more, 0. And then let me give another way of describing the same set. In terms of valuations, another way of saying this is, well, M, yeah, unrelated. You have a boundary divisor with a weight, with a positive integer weight. So it's a pair of a boundary divisor in some compactification with a positive integer weight. I can describe this another way. Well, maybe I could have said for some people, these are what you would call, well, except for the weight, these are essentially the log canonical centers. Centers for omega. That would be the Mori theory way of putting it. Or let me give you a different definition. So let's say I have a variety Y. It's going to be a minimal model when I use it here. And let's let Q be the field of fractions, the meromorphic functions, the function field. And let's say I have a divisor on here, an irreducible divisor. Well, I get a certain function out of each divisor, a function on the field. I'll get the valuation with respect to E as a function from the field of rational functions to Z, which just takes f, a function to a non-zero function to its order of 0 or pole along E. So just the order along E of f. So just the order of 0 or pole. Of 0 or pole. Well, these functions, you can characterize these just purely in terms of this field. In terms of the field. These are what are called divisorial discrete valuations. This is what are called divisorial discrete valuations of the Q. And so in terms of this, I can define this thing kind of obviously. What is this? This is just a divisor. That's just a discrete valuation of the field. And what's this condition that it lives in the minimal model? I could say this is the set of V from Q of U to Z, which are these things, these discrete valuations, divisorial ones, such that what condition? The fact that it corresponds to a divisor in a minimal model is exactly that the valuation of this canonical volume form should be negative. But then add in the 0 valuation as well. If you think about it, it makes sense to ask, if you have a top degree form along a divisor, you can ask what are the orders of 0 or pole of the form just as well as you can a function. So this is a perfectly natural object. And this is going to be the parameterizing set for the canonical basis of functions on the mirror. So the goal will be to take just the vector space V, just to be a vector space with this basis, with basis this tropical set, U trop of Z. That's, in other words, take the direct sum. So I'm going to take, given a Calabi-Yau, I'm going to just take the vector space which has this set as its basis. U trop Z. I mean less than 0. It turns out that it's a cool thing that happens with log discrepancies. You can ask your boyfriend about that. Because of the condition, it's actually, if it's negative, it's only -1. It never becomes less. So M is because, good question. A valuation you can multiply by a number.
Okay, so it's M minus M then?
No, it's just less than 0. It has this is. Let's let this go. Think of it this way: it's just a boundary divisor with a number attached to it, a positive number.
Well,
Think of this as a linear variety minus theta divisor or some power. Do we get the same?
No, that will not be Calabi-Yau in this sense. I'll give examples in a second. That's not a Calabi-Yau, anything like that. That's a general type. So if you take vector space with this, so I'm going to take what I'm going to do in this talk is I'm going to take the vector space, which is just. So this is, I usually write this first, but what I mean, just take the vector space with this basis, namely this, and then I'm going to put a multiplication rule on it. We're going to show it has a natural multiplication rule, has a natural multiplication, so that it becomes a finitely generated C algebra. And then I'll show that the spectrum of this, and then spec V will be the mirror. Will be the mirror. Now, people in the know that the mirror is not a variety, it's a family of varieties, but I'm going to leave that along until I define the multiplication rule, and we'll just see when we define the multiplication rule that, oh, we shouldn't have taken constants here, these should be coefficients. So for the moment, we're just going to take a vector space, this natural vector space, I'm going to put a multiplication on it, and that'll be the mirror. Yeah, just a symbol. I'm just saying it's a vector space with this basis. Yeah, that's just what it means. Okay, so now let me give you examples. So what are the examples?
Why is n positive?
I'm just defining it to be positive. It's a set. You mean here? I just defined this to be the set of such things. A boundary divisor together with a positive number.
And the positive number is determined by?
No, it's a set of pairs, E comma M. So it's a product. Okay. Okay, so let's take, for example, so first the first example, let's take U to be C star to the R. So an algebraic torus. But a torus has two lattices associated with it. Anybody who plays with rhetoric varieties. So let's say so my notation is Tn. That means n tensored C star. So here n is Z to the R. N are the co-characters. NR, I think you guys, I get the sense you do a lot of toric stuff. NR is where you draw the fan. Where you draw the fan for a Tn toric variety. So the first example is just this. And what's the volume form is the one you know. dz1 over z1 wedge dzr over zr. What are the minimal models? YD, that's supposed to be a compactification of the torus. YD is a minimal model if and only if it's toric variety. If and only if it's a toric compactification. It's easy to show. So for toric varieties, for the torus, a minimal model is just a toric variety. I mean, it has to be compact. That's the only condition. And what's this tropical set? What's Tn? So I take the torus. What is this tropical set? Well, the claim is that it is just canonically the set N itself. So that's the cool thing once we see this. Now I have a way of, the torus has this lattice associated with it, but now I'm saying that every Calabi-Yau has an analog of the lattice. So why is this true? I bet most of you will get this who've done the toric stuff. So what I want to say is, let's take a point, take some V in N, and let's, for the sake of, just for this, let's say primitive. And what am I supposed to do? The claim is that associated with this, there's a boundary divisor in a minimal model. And I already told you that means a boundary divisor in a toric variety. Well, so let's do the case where n is Z2. And let's draw the picture. So what do I have? I give you here's 0. I give you a vector in Z2. Let's take this ray. Now, maybe you don't ever study the toric variety just given by this single ray. But at first you usually study kind of a complete toric variety just because those are more interesting things. Doesn't matter. Take this complete toric variety. What does that give you? It gives you some kind of surface that looks like this. 1, 2, 3, 4, 5. It's a surface. There's a torus. C star squared is the inside. That's U. Here's the Y. And what's D? The boundary divisors correspond to exactly the rays. So here's E sub V right there. So that sets up this thing. It's just that was a primitive one. If I took 5 times it, I would just take 5 times it. So that's just it. So that gets the correspondence. I could also have shown you how is it that I could have also done it in terms of valuations. That would be sort of totally tautological. How is it that a point in, what are the functions? Well, maybe let's say that also. What are the theta functions? Where does this come from? Well, what are the functions on the torus? What are the natural functions? Well, those are the characters. Well, this n is the dual lattice, so just canonically they are valuations on the dual characters. Let me do it the other. Let's see what are the theta functions. So the vector space V, I'm saying in this case we should take the direct sum over Q in n of C times theta Q. Well, what's this? So the claim is that this has a natural multiplication on it. Well, this is just the dual torus. Let's take the global sections of U star, OU. So this is the dual torus. The dual or mirror torus. What's that? That's maps of n into C star. That's how you define it. So, of course, And these are just the characters. I mean, these are the characters of U star. So these are just Laurent polynomials. When you write the thing down in terms of the dual, these are just Laurent polynomials. These are Laurent polys on the dual torus. So of course, this is indeed the global sections of U star, OU star. So of course, this does have a multiplication. But the thing to observe, let's just observe that in fact this is canonical. So the monomials, I'm saying that the monomial basis of functions on a torus is actually a canonical thing. It's intrinsic. It does not depend on any choices. So just the claim here is that if I take a torus, so the remark, which was part of the inspiration for this, remark is that if I take U to be C star to the R, then the characters, which are, the monomials, the monomial basis, the monomials, they're of course a basis of the global sections. But the claim is that this is actually, they're intrinsic. How come? Well, just a little lemma, that these are the invertible functions. F in global sections of U, OU is invertible if and only if it's a character, well, up to a scaling. F is lambda times some, I'll say theta q, where this is a monomial. We're just saying the only polynomials that have no zeros or poles on the torus are the monomials up to a scalar. That gives you this canonical basis. Let me just note, for example, just by contrast, let's take C. I would say that C, or better even C2, is even more exaggerated, but take C. I would say the global functions on C have no basis. What are the global functions on C? Well, it's polynomials in one variable. That has a basis, 1t squared, but let's say 1 t minus 3 squared, that's just as good. And if you took C2, it would be much worse. Basically, there are just way too many automorphisms of Cn for it to have anything canonical on it. It's just a totally homogeneous thing. But it's sort of surprising that the torus, and notice this doesn't use the multiplication rule when I say the torus. It's really a torsor for the torus. You have this canonical bunch of functions. Where did that go? Right here. Okay, so that was my first example of a Calabi-Yau is just the torus. Let's give you a non-toric example. There'll be loads of those. So some non-toric examples. No, so when people are doing that's a compact Calabi-Yau, right? When the people so far, don't be confused by that. People, so here we're doing these things like taking a reflexive polytope, taking a hypersurface in there. That's a compact Calabi-Yau that lives in a toric variety. For me, it's not the toric variety is the minimal model, is a compactification of the dumbest possible Calabi-Yau, which is just the torus. So that's the world we're in here. So let me give you an example. So to get a non-toric examples. No. The answer is no. That's a compact Calabi-Yau.
No, he asked about toric Calabi-Yau.
Oh, what does toric Calabi-Yau mean to you? That doesn't mean a hypersurface in a toric variety. Oh, it just means a torus. Yeah, so it's a torus, right?
What about this maximum boundary condition?
Yes. Of course, if you take a toric compactification, take C star squared, compactify it to CP2, has a triangle on the boundary. It has a zero stratum where the 2 points meet. Does everybody see that? Take C. Yeah.
Whether any toric Calabi-Yau.
Let's talk afterwards if you don't mind. So non-toric examples. Well, basically there's millions of these things because if you take any example, there is a sort of infinite number of blow-ups of it that are also examples. So let's take, for example, CP2 or any toric variety. Let's take Y bar D bar toric surface. Complete toric surface. So here I'm drawing the picture of CP2 with the coordinate axes, x, y, z equals 0. So CP2 is the blackboard. These are the 3 coordinate axes. The torus is the interior. And now blow up any number of points you want on the boundary. And let's take y to be the blow up at any number of points. And then, so what does the picture become? I'll have, I throw in a bunch of these -1 curves wherever I blew up. I'll draw 6 because that'll be some classical thing. I blow up this, and then I take D though, to be the strict transform of the toric boundary. So that means it just goes isomorphic. So D goes down to D bar just as an isomorphism. So in this picture, I'll make that the bold thing here. That's just still the triangle. So by this process, I made Y bar bigger. I blew it up. I didn't make D bar any bigger. So therefore, I made the complement bigger. So I let U now. So U is now Y minus D. And by construction, inside of here, I have Y bar minus D bar. That was the torus. But notice, what did I add? Well, what did I add to Y? I added all these CP1s. But then I throw away the triangle. So what I added to the torus was the CP1 minus this 1 point. So what we get from this is that in this case, U, the example U that I have, U is C star squared, disjoint union a copy of C, or A1, for each point, for each P blown up. So for each point, I added a C star. What's the tropical set in this case? So this still has maximal boundary, obviously, because it has the same boundary as the previous one. These are maximal boundary. Note, if we have
A C or a C stars?
a C, because I added a P1 minus 1 point. Note, if I have a torus living as an open set in my U, and this is Calabi-Yau. Suppose I have that situation, which is what I have in the one I just constructed. Then look at the definition. Well, I guess you can't. I erased it. But what was the definition of the tropical set? It involved the canonical volume form. There's only one volume form. So the volume form here is just the restriction of the volume form here. So they're sort of, well, I'll just say that they're equal. And notice that they have the same field of fractions. They have the same function field. They have the same meromorphic functions, because one is an open set of the other. So my tropical sets are just the same, because the tropical set was defined just canonically in terms of this and this. So the tropical sets are the same. So Tn trop of U of Z is just equal, at least as a set, and that's the only structure I gave to you at the moment, trop of Z. They're equal, but let me say that I won't have time. I won't take the time to describe this. This has a more natural. I could also do this with real numbers. I could take real things, and then this is naturally a piecewise linear manifold. Actually, what's called an affine manifold. This is not equality of linear things. It's equality of piecewise linear. So let me explain what I mean. So what I want to say is, this was n, which is z to the r. But I want to be clear here that this does not have an addition on it. Does not have any plus. This is not a lattice, because, canonically a lattice. Let me just explain why. What almost always happens if you have one torus in one of these surfaces, or one of these varieties of any dimension, is you have infinitely many. This is the theory of cluster varieties. It's kind of surprising. I think it was first discovered by Luenga that you produce. I made this blow up in order to produce one torus. There's actually a whole Weil group, and usually infinite Weil group that is there's a Weil group's worth of other tori. And then there's the cluster tori. Those are actually a different bunch. There's two different infinite groups of tori in the same one. So let's suppose we have that situation. Suppose I have U, and I have two toric open sets. They're the same torus living in there in two different ways. They're both open sets. Then what do I get out of this? I get a map from n, which is T1 trop Z. That's the same as U trop Z. That's the same as T2 trop Z, which is the same as n. And this is an isomorphism from n to n. I get this isomorphism. But this, if you write down the equation for it, this will be a piecewise linear map, not linear. So this will be piecewise linear. And it will only be linear only if they're equal. Only if and only if T1 is equal to T2 as subsets. As subsets. This is where all the piecewise linear things that come in the tropical world is by this process. If you've seen go ahead.
Remind me, what was the definition of T-trop?
Yeah, so any trop, is it still here? The definition of the tropical set is, it's all the valuations of the field of the, what's that?
In T-trop.
Yeah, there's a trop of any Calabi-Yau has a trop. So T is a Calabi-Yau. It's a torus. So I'm applying the definition of trop to two different Calabi-Yaus, U and to T. So here I have T. That's C star squared, for example. That's a Calabi-Yau. And in this picture, it's living as an open set in my U. They're both Calabi-Yaus. They have actually the same volume form. The volume form here restricts to the volume form here. The definition of the tropical set is it's the valuations of the function field where the volume form has negative valuation. Notice that's just the same as a set between the two. But it's not there. But what I'm saying, so that might, and in this case, as I explained, it's just a lattice. The tropical set is a lattice. But if I have two different open sets in the same torus, I will get two different identifications of U trop with a lattice. They are not compatible. I'll get a piecewise linear map from the torus to the torus. How many people have seen cluster varieties? Well, there's piecewise linear mutations that occur there. This is where they all come from by this process. So these are the so-called cluster mutations. It's a piecewise linear thing. It is piecewise linear, though. So what that means is I could have done this with real numbers. Then I would find out that this is a piecewise linear manifold. It does make sense. So you can't add. It does not have any addition, but it does have scalar multiplication. It does have scalar multiplication. Scalar multiplication, at least multiplication by an integer. Multiplication by an integer makes sense in the tropical set because it's a lattice up to a piecewise linear map. And why do I mention that? Because when I gave the definition, it might have looked a little hokey. I just threw in this extra point 0. I just said, do this junk, throw in 0. That's a canonical thing, that 0. So scalar multiplication, by a positive integer makes sense. Makes sense in U trop. So 0 inside of U trop is indeed a canonical point. That's a canonical point. So there really is a special point in this space, which is the 0. Yeah, I mean, I could have done this over the reals if I took real valuations, and then it would just exactly scale down to the 0. Okay, so what you should think of for these simple examples is like take the example of P2, blow up 6 points, you'll get what's called a cubic surface. You blow it up, here you get YD, which is now a cubic surface because it's P2 blown up in 6 points, plus a triangle of lines. And U is the complement. Y take away the D. This is actually what Keel studied in the 1860s. This is an affine cubic surface, what's called an affine cubic. It lives in C3. It's given by a cubic equation. And what you should think of is the tropical set. I have this set. It's non-canonically Z2. It's equal to Z2, but you could have also thought of the real. It's a subset of a real manifold, which I didn't define. Didn't give you the definition. This is homeomorphic to R2, but only as a piecewise linear manifold. So it doesn't have an addition naturally on it. Okay, let me give you one more example to show that these things really matter. So here I just showed you could produce millions of these by blowing up. These all have maximal boundary, these things. Other examples are all cluster varieties. All cluster varieties, of which the most interesting example is to take the character variety of a Riemann surface. Take Hom of pi1s into SLMC, or any group, SLMC, where this S is a punctured Riemann surface. Punctured Riemann surface. At the end, if there's some time, I'll come back to say a little bit about this example. Here I just wheel it out to show you that these things are significant. This is the so-called Hitchin system. It's like one of the most studied objects in geometry is an example. So these kind of Calabi-Yaus really do matter. No, you can do both. If you fix the conjugacy classes, that's Calabi-Yau, and the total space is also Calabi-Yau. So you can do both. In the world of, well, I'll mention when we get to it. Okay, so here we have examples. Now, all the examples I gave you so far, and which are the only examples I'm going to give, they all have a torus. This is a torus, living as a Zariski open set inside of U. In particular, U is a rational variety. It's birational to Pn. Birational Pn means you have an open subset which is also living in Pn. So these are all rational. There's no reason, I just want to tell you, these are a tiny fraction of the examples. Most will not be rational. So most are not. it's sort of the, these are what are called, another definition for my Calabi-Yau is basically log Kodály dimension 0. These are the analog of, when I say that most of these are not rational, it's like the statement that most Fanos are not rational. It's that's just a tiny piece of these things. Okay, so there's loads of these guys around. All right, now let's go back to trying to construct the mirror. So maybe you want to construct the mirror to the affine cubic surface. Or you could take the simplest possible example of this is, let me give you an even simpler example to get your head around. Take CP2 to be y, and take D inside of here to be a singular cubic with only nodes, with nodes. So there's three things you could have: 3 lines, line plus conic, or an irreducible nodal cubic. Take that to be D and take the complement. So I'm saying that thing has a canonical basis of functions on it that I want to describe. Okay, so now the goal, so now that we've understood this thing, is to take V to be just this vector space, Q in U trop of Z, of C times theta Q, and I want to make this into an algebra. I want a natural multiplication. Why? Because I'm going to then say that the spectrum of it is a Calabi-Yau, and that will be the mirror, just like it worked in the torus case. So I want to produce the dual. Then spec V is going to be the dual. Spec V should be, this isn't defined, U dual, the mirror. So how do I put a multiplication on here? Well, notice what's one feature of this that's true about this vector space already. As I said, this vector space has one distinguished point in it. Has this 0 point, which is a special point. So this vector space comes with a map to C. So V has a canonical map to C, which I'll call the trace, which is just take the coefficient of this distinguished basis element that's associated with the point 0. No arguing with that. Now, this is supposed to be the functions on an affine Calabi-Yau. That's my guess, right? So what I'm saying is that every affine Calabi-Yau should have a canonical map to C. The function should have a map to C. So now I'm saying this implies, the conjecture implies that given U now, as above, there should be a map from the global sections to C. There should be a kind of trace map. So what is this trace map? Well, so we constructed this thing just with this abstract trace map, and then I asked David Ben-Zvi, what could be this trace map? And he said, well, if you have this canonical trace map, it means a Calabi-Yau, there must be some cycle that you're integrating over, which we should have thought of a long time before, because in mirror symmetry, there is this most important cycle, the SYZ fiber. So the claim is, there exists a canonical homology class in this thing, in the middle homology of U. So let's see where this comes from. I haven't used my maximal boundary condition yet. That's where I'll use it. So let me explain what this class is. Oh, and then the trace is a function goes to the integral over gamma of just take the function and multiply it by omega. So that's what, the philosophy is, if you have a trace, you ought to have a cycle. It should be integration over a cycle. So what's this cycle? Well, what does maximal boundary mean? Maximal boundary means that there exists a minimal model YD and one point. So the picture might be something like this, the two-dimensional picture. I have some point, which is a point where two of the boundary divisors meet. So locally, analytically, I have P. I have the picture at P of Z1 ZR equals 0, the coordinate planes sitting in CR. Well, there's a little torus there that lives in where the Z's are not 0. So let's take gamma to be where the coordinates are just small. The conjecture is that this class is canonical, is canonical, independent of the choices. I.e., first it's independent of the minimal model that I choose. There's infinitely many minimal models. You, for example, can just blow up this point and get another minimal model. Independent of the minimal model, and given the minimal model, independent of the zero stratum, P. So here there's all these different guys, and I would take this little analytic torus that only makes sense analytically locally at this point. The claim is the class I get is unique. So all the conjectures I say are theorems in dimension 2. Let me mention that 1 is true always. Theorem, so 1 holds. No, 2 holds. 2 holds. And I think it's quite a deep thing in birational geometry. It follows from what I call the Shakurov connectedness, but I think Janos would call it Janos's theorem because it was proved by Janos. So, so 2 holds, this is by a recent theorem of Janos, theorem of Kolar, which has all sorts of surprising information about this manifold, which I didn't define. I only defined the z points of this manifold. If this u trop r a priori should have no properties, like you might wonder, could this happen? Could I just have a picture where the 0 strata or worse would be something like this? What if these 0 strata are sort of disconnected from each other? How could I possibly compare the picture here to the picture here? All kinds of topological questions you would ask. The thing has very special properties, the boundary of a Calabi-Yau. But anyway, so by Janos's theorem, this is true, and then in dimension 2, this is easy. I'm sure it's true always. The thing.
Isn't this class defined only up to sign?
Yeah,
Because if we write it down in a different order, it changes orientation. That's same as computing Poincare residue. So the only.
Yeah, so actually, in dimension 2, we actually do choose an orientation of the boundary throughout the whole thing, which is, yeah, because it's always just this, all the middle models are just take this one and blow up a point.
But it's not the automorphism of the torus. If the torus, you take the automorphism, you keep one and the other.
No, I think you will get,
I think the SL2Z automorphism
yeah.
Right, versus the GL2Z. So I think that.
Yeah, I think it takes it to the minus, this class. Yes. So maybe up to orientation, canonical. So what is it good for here? We can now fix, at the beginning, we can first of all fix omega, which was only defined up to scaling up to this point. Now we can get rid of the scaling by requiring the integral over gamma of omega to be 1. But now more importantly, now I have a natural trace function. So I go from the global sections of u, OU, to C, just by f goes to the integral over gamma of f times omega. This is a top degree holomorphic form, so it's closed, so this makes sense. I have this map, and I get more. Now I get a sort of Frobenius algebra. I have a vector space with a trace, and the vector space has a multiplication. So I get a k-point function also. K-point function, which is just, I'll define it this way, f1 up to fk. You always have this when you have an algebra. It's just the trace and the trace of the product. But again, what does that mean? These are a bunch of functions on the Calabi-Yau. It just means you integrate over this special cycle f1 over fk times omega. So I take the trace of this thing. And now the conjecture, again, theorem in dimension 2, is that the 2-point function is non-degenerate. Non-degenerate. Now, what does that mean? This is an infinite dimensional vector space, of course. It's like it's a coordinate ring of a variety. Non-degenerate meaning that f, the function f, is determined by the inner product, by the functional f. Just the map. You can't ask that the map to the dual be an isomorphism in an infinite dimensional vector space, but you can ask that the map to the dual be injective. So the map from V to V dual is injective. Now, why is that interesting? Well, it's what allows me to give this talk in a totally elementary way. The actual way we define the algebra structure on this uses some fancy machinery. But surprisingly, when we rephrase the multiplication using this bilinear form, it becomes more elementary. So notice what this says. So by the conjecture, the multiplication rule on the vector space is determined by the 2-point function and the 3-point function. Because suppose I want to know what f times g is. I need to know this. But this, by very definition, is just equal to this. So f times g will be the unique thing that produces this linear functional. So this is how you do it in quantum cohomology anyway. You people probably this looks natural anyhow. But I can just as well define the multiplication in terms of telling you the k-point function. Okay, so now let's go back to the this was sort of motivation. Let's go back to the goal and try to define this multiplication. So now we're back to, so again, U is just this Calabi-Yau with maximal boundary, like an affine cubic surface or the complement of a nodal curve in P2. So U is this Calabi-Yau with max boundary. And I'm defining the vector space V just to be the vector space with the tropical set as basis. U trop Z of C times theta Q. And I have a trace. I think I called it, well, we'll call it V now. I have a trace function, which is just the coefficient of theta 0. Coefficient of theta 0. And I want a k-point function now, which should be, multilinear. Multilinear. Well, since it's multilinear, and I have a canonical basis, or I just have a basis, I just have to tell you what to do with the basis. So we just need theta q1, theta qk in C. It's actually going to be a number. It'll be in Z or in Q. So how do I do that? So I have to give a bunch of these. These are just a bunch of points of the tropical set. I want to get a number from them. Well, what is this again? What does Qi mean? Qi is just this pair. It's a boundary divisor in a minimal model and a positive weight. So I can draw. So let me draw a picture of this is what you're given. We're given a bunch of these things. So let me draw the picture in dimension 2. Picture in dimension 2. There, the boundary is always this cycle of rational curves that I keep drawing. So what you're given is, you're given a minimal model. You're given some minimal model, and you're given a bunch of boundary divisors with weights attached. Some integer. So I have the divisor and a number, maybe E3, M3. And I want to get a number out of this picture. So what I do is I count curves, rational curves that look like. So what I do, first fix a general point. General. Here's my point Y, and then I take rational curves that look like this. So what does that mean? It means I consider maps of P1 with k plus 1 marked points. I'm doing the k-point function, so I have points x1 up to xk, and then one more point, I'll call it star, into Y, which look like this. The inverse image of D will be k points with the given multiplicities, and this point star goes through the point Y. The fun thing is you just look at the naive dimension count that you get for this thing, which I'm almost positive in these cases is actually equal to the space. I think in this case the space has the right dimension. The dimension is, just by naive Euler characteristic calculation, the dimension is k plus 1 minus 3, which is the dimension of M0 k plus 1. So I have a P1 with k plus 1 points. The set of maps I have are exactly the moduli space of P1 with k plus 1 points. So that means if I fix the cross ratio, if we fix the modulus just of this P1 with these points, as a fix this in M0 k plus 1, then I get a zero-dimensional space. So what would that mean? That would just be the cross ratio, in the case k, cross ratio of the 4 points in the picture that I drew of the 4 points. So in this picture, I have 4 points on my P1, fix the cross ratio of those 4 points, then I'll get a number. I get a zero-dimensional space, and so a number. And so a Gromov-Witten number. And now I want to say that's my number. Except, now I told you that, and this is good, if I'm constructing the mirror, I don't want one variety, I want a family. You can't just count rational curves. You have to fix the homology class before you can count rational curves. So it looks great. I've got this thing. I'm going to get numbers, but I have to throw in the homology class of the curve. I want that in there anyway. So what I really need to do is, you need to do Gromov-Witten, just to count, you have to fix the topology of the thing. So to count, you have to fix a class. It would live in the homology of Y, but actually it will live somewhere else. Naturally, it will live in the Mori cone, because it is, after all, the class of a Riemann surface. So this will live in the Mori cone. This is just if you didn't know the definition of the Mori cone, you would just discover it here. It's not any old homology class. These are just the homology classes which are the class of a curve. Take the group, not the group, the additive subset generated by those, the monoid, the cone. So this is the cone generated by classes of curves, which if you define a curve to allow it to be reducible, that is just the class of a curve. So it's the classes of curves. And then the right object to take is, I should take R to be the functions on the associated toric variety. So I should take my ground field. I'm taking C, but this will work over any ground field. Take the associated monoid ring. So what does this mean? This means I take the functions, the global functions of the toric variety given by this cone, Fy. So take the cone, the dual, that's the Neff cone, that's a cone. A cone gives you an affine toric variety. The functions on this affine toric variety is exactly this thing. Just what is it as a vector space? It's just the direct sum over all the curve classes in this cone of C times a vector, it has this as the basis, but the multiplication is the obvious one. Z to the C times Z to the C prime is just Z to the C plus C prime. These are just monomials. They're a subset of monomials. So I take this ring, and now notice, what do I need to get this number? So if I just fixed, so given Q1, Q2, up to QK in the tropical set, that's a bunch of these, that's these, EI with MI, a bunch of these things, and C in the Mori cone, I get a number. Well, what that means is, if you just repackage it, what that means is that I should really take, the right way to deal with this is to just I should take instead of just redefine V to be the direct sum over Q in U trop of the free R module, R theta Q. And now I have a map, a K-point map to R, just as I just defined. That's exactly what it means. That just is exactly what I said. So I get the K-point as defined. I don't know, is it obvious? What I'm saying is, if I want to tell you what theta Q1 up to theta QK is, that's an element now of this direct sum over all curves of some number times the curve class. I just told you what the coefficient of each curve is. The coefficient of the curve is the sum. So notice, by the way, for people in the know a little bit here, what's the associated torus of this toric variety? The structure torus for this toric variety is what I call T pic of Y. That's basically the complexified Kähler cone. This is the complexified. The complexified Kähler cone would be a tube domain in there. Complexified Kähler cone. So that's what I want to have be the coefficients of my mirror anyway. That's what should appear here. Okay, so now let me state the conjecture / theorem. Say again? Say what? Oh no, the rational curves. Count rational curves that look like this. Maps of P1 into Y. Although it could well be that a curve that is like this is automatically rational. Like if it only meets once, it's rational. Go ahead.
Are you also supposed to make a conjecture what any bar Y looks like in this case?
Say it again?
Are you also making implicit conjecture about what any bar Y looks like?
I haven't put in my condition that U is affine. So now this actually works. The definition I work here works without affine. Let me leave it as, how will I say that U is affine? I'll say that the boundary supports an ample. Then Y with D will be a log. It will be a log Fano. So it's guaranteed to have good. It has a good shape. We can talk about it afterwards. But yeah, in the case that when U is affine, YD is a log Fano, and this is a finite cone. All right. So what's the conjecture? So conjecture and theorem in dimension 2. Is that, so first, there exists a unique finitely generated commutative associative R algebra structure on this set V, which was my direct sum, such that, well, the first thing is I want theta 0 to be the identity of this, my special basis element. I want that to be 1 in the algebra. I want that to be the multiplicative identity. And then the second condition is I already have the trace function, right? I've already got the trace on V. That's just take the coefficient of theta 0. I want my k-point function, which I already defined. That's the k-point function, which I just defined by counting rational curves. I want that to be the trace of the product. And then part of the theorem at the end will be that, or conjecture will be that this is also has an interpretation as that's integral that I gave before. So that's the first statement. The fact that it's unique includes the fact that this is unique is basically the statement that the 2-point function is non-degenerate. So okay, suppose I have 1. So what I give you here, just to be clear, I just wrote down a vector space, or this free module, and I just told you how to multiply on it. That's really where we're at. I just gave me a Calabi-Yau, I just told you how to multiply. So now I can look at X, I can take the spectrum of this algebra, V, and it has a map to spec R because R is a subalgebra of it. This is guaranteed to be flat because this thing is a free module. So this is a family. This is flat by construction. And the conjecture is that this is a family of, I'll just say this because this is technical and then I'll make it more, this is a family of k-trivial Gorenstein SLC varieties. So it has very nice singularities. But, and I'm happy about this because this is a toric variety with a big boundary, an F cone for Y. But let's make it, inside of here I have the torus. Let's restrict the family just to the torus. The conjecture here will be that this is just an ordinary family of Calabi-Yaus. Pi is a family of affine Calabi-Yaus with maximal boundary. Affine Calabi-Yau R folds with maximal boundary. Homological mirror symmetry dual to U. So that's the conjecture, is that when you do this, you get the mirror. And now I always wondered, what is mirror symmetry good for, just for an algebraic geometer? Because what is it, when you first hear it, what does it say? That the bounded derived category of the variety is equivalent to the Fukaya category of the mirror. Which to me was that one thing that I'm uneasy about, the derived category, is equivalent to something that I'm absolutely terrified of. And I thought, who cares about this? And you guys liked it. I used the same joke in England where all those guys studied the derived category. And they all just stared at me like, what sort of freak are you? That, they thought, what? So anyway, that's this. But let me say, now why is this thing cool? Even if you don't care about mirror symmetry. So let's continue the conjecture. So that's up to 2. 3. So let's take V. Well, unfortunately I can't. Okay, I'll have to call it W. Let's take W, a general fiber of this family. So it's a Calabi-Yau with maximal boundary of the same dimension that I started with, an affine Calabi-Yau. So it has all the conditions that I need to run the program again. So just do it again. So run the same thing again. And I'll get, I'll take the direct sum of now points in W trop. Maybe call this V star. The conjecture is we get the universal family of deformations of U. But now with a canonical basis of functions. But now each fiber has theta functions. It has exactly what I claimed at the beginning. A canonical basis, this canonical basis with multiplication rule given exactly as I said by counting rational curves. Rule which counts rational curves, counts rats on the mirror. So even if all you care about is, let's say you're Cayley, you're studying the affine cubic surface, what you find out is, so there are infinitely many cubic equations that give you the same affine cubic surface. But this says one of them is canonical. There's actually, the cubic surface lives canonically in C3. And so does all sorts of algebraic varieties have these canonical functions on them. Okay, so that's 3. 4, part 4, is that this algebra is actually known already that my vector space V, which is an algebra, is what's called the symplectic cohomology of U. This is what I really like because I had to listen to a lot of talks about symplectic cohomology in my early days in Texas. And they were always talking about how impossible it was to compute this thing. And every example they gave was an algebraic variety. And in fact, the ring they were trying to compute was the coordinate ring of the variety that they were looking at. So it's actually the easiest thing to compute. It's just every example computes itself. It's also very good for us because the hardest thing to prove in this conjecture is the associativity of this multiplication. This is already an associative algebra. So this is nice to have. This we haven't proven. Everything else is a theorem in dimension 2, but not this. A postdoc of mine, a smart guy, is working on this. Finally, let me make one thing that people might have noticed here. Let me just say a word about it. Notice it's not quite satisfying because I produced this family over T, pick Y. You might object because Y is an auxiliary thing. I start with U, and Y is a blow-up of, Y is a compactification of U. And its Picard group could be infinitely big. I could take a torus and compactify it to any toric variety. I could have an arbitrarily huge thing. Now, I do have a modular meaning for this family, but I won't describe it. But what's actually true is, if you look at this sequence, pick Y goes to pick U, and take whatever the kernel is. It's generated by the boundary divisors. You get a corresponding map of tori. And we call this torus the relative torus. What you can show is the whole construction is equivariant. The construction is TD equivariant. That's clear from just the definitions. So you can take the quotient by the relative torus. You'll really get a family over this. And that is completely independent of all choices. OK, so finally, let me give you an example of what these theta functions are. In a concrete example, let's do that cool thing let's do an example. Let's take U. Well, I'll call it X now. Let's take the Hitchin system here. So pi1 of S into, let's do SL2C mod SL2C. And to be concrete, let's do the case where S is S2 minus 4 points. So the first cool thing, this is due to Fock and Goncharov, is that the tropical set, which they defined slightly differently, but it's easy to show it's the same as what we have, that X-trop is something that people, Teichmüller people study. This is what's called the space of laminations. These are integer laminations. Integer laminations. So what's an integer lamination? This works for any punctured Riemann surface. So here's my Riemann surface, maybe with a few punctures. A lamination is just a bunch of isotopy classes of disjoint loops with numbers attached. So that's what a lamination is. A bunch of isotopy classes of disjoint loops, each with a weight on it. So that's what this set is. And now let's look at this, and in particular, and now note, so what's the claim? The claim is that each point of the tropical set is supposed to give you an absolutely intrinsic function on the variety, intrinsic to the geometry of the variety. Well, let's take a simple loop, for example. Let's take gamma in X-trop, Z, just a loop with weight 1. You can easily generate it. So what do I have? I have a Riemann surface, and I have a loop. And I'm looking at the space of representations. So what's a point in this space? It's a map from the fundamental group into matrices. So here's a loop. That's an element of the fundamental group. I get a matrix up to conjugation. If I take its trace, that makes sense. So I have the sort of the trace of the monodromy. So I'll call that just trace sub gamma, which means take the trace of the monodromy. Trace of the monodromy around gamma is an obvious function that you have on this space. So a theorem only, So in particular, because I have this punctures, I have some distinguished loops, basic loops around the punctures. So you get a map of X always down to C to the number of punctures. And now let's do the case with S2 and 4 punctures. So for S2 with 4 punctures, the theorem is this is our space. This is our universal family. Our universal family. It's also Cayley's universal family of affine cubics. And it's also Cayley's family. Cayley's family. He had it in the wrong coordinate system, but he doesn't have it in the canonical coordinates. But just in coordinates, this X sits canonically in, let's call this base S. That's this torus, which is the base. This is S cross C3. It's given by equations x, y, z equals x. No, S is, sorry, bad, just t, the base. It's the c to the number of punctures. X squared plus y squared plus z squared plus ax plus by plus cz plus d. So this is what an affine cubic is. It's a zero locus of something like this inside of C3, where these are the parameters. Those are the 4 parameters. You have 4 parameters. So that's an affine cubic surface. So the theorem, which worked out with Andy, is that in this case, the trace around gamma, so gamma gives me an element of the tropical set. On the one hand is identified with integer laminations. Therefore, it has a canonical trace function. But on the other hand, it's the tropical set, and so it has an intrinsic function that only the manifold itself knows about, independent of the modular meaning. This is equal to theta gamma. So to me, this is just really surprising. This says, for example, that the trace function is intrinsic to the underlying manifold of X. You don't have to know that X is a moduli space. For example, Keel did not know that the cubic surface was a moduli space of matrices. You can describe this thing as just, in that case, as 4 matrices, that satisfy some rules. People at the same time other people actually knew that we're studying this family from the point of view of matrices. But Keel had no idea. The fibers of this are just affine, they're these things. They have intrinsic functions on them. Those intrinsic functions turn out to be these traces. So the trace is intrinsic. To me, that's just wild. That this thing that looks like it has everything to do with realizing the cubic as a moduli space is actually completely intrinsic to the cubic. Okay, that's it.
Given the time, do we have any very quick questions?
So, is this a statement about infinity structures being the same?
No. No, nothing about that. I like about this. We don't have to get into the A infinity structure at all.
Isn't the statement that the Hochschild homology of the both sides are the same? Yeah?
No, this is just by itself. For me, that's just a ring.
Yeah, but it's also the Hochschild homology of the guy's side of.
Well, I mean, yes. In fact, yes. Sorry. What's actually true after we did this thing, then we were showing people this ring, and that guy who left, he and some other people suggested to us that this looks an awful like symplectic homology. In fact, if you look at the mirror symmetry conjecture in this context, you will get this conjecture out of it. That spec of this ought to be the mirror. So I'm sure that whatever is expected from mirror symmetry is true. We won't have proven it. We just have proven this one thing. We haven't proven this is that this satisfies homological mirror symmetry. Oh, I should say the one case where it's known. It's possible that this is the underlying point of your question, but probably not. The one case that we know is actually due to Ludmil and some other people, where they computed the mirror to one of these families, and we checked that we indeed get their family. So
let's thank the speaker again. And we'll make the next.